Unit 3 now, investigating infinite sequences and series. So we'll start off with the introduction to sequences. All right. We discussed this somewhat in the first unit, right in the very beginning, but hadn't really come back to it since. So what we're going to learn how to do is define a sequence and then determine there's interesting characteristics of sequences and series. There's so many things to list that if I do it now, I'm stealing my own thunder. All right, so definition of sequence is a function whose domain is a set in the form of n belonging to the set of positive integers, or n is greater than or equal to n, where n is a positive integer. All right, so the little blurb here, up to this point, we have worked with functions of a real variable. That is, the domain of a function was either the set of real numbers or was a subset of the set of real numbers. So we have a sequence here, which is the domain of the set of the sequences, the positive integers. And you could see that it's the value of f of n is reliant specifically on only positive integer values, because that's how we defined it. All right, so each one of these elements would be a term of the sequence. All right, so what we need to do, and if you just follow the notation at the bottom there, you see how that kind of plays out. What we need to do is learn how to expand sequences, but also learn how to develop rules that can be used when dealing with a sequence that's already expanded. So if you look at the bottom here, you see we have this general relation where it says f of capital N, f of capital N plus 1, and so on. If n is equal to 1, then our first entry would be f of 1. Our second entry would be f of 1 plus 1, f of 1 plus 2, f of 1 plus 3, and so on, all the way up to f of 1 plus n minus 1. All right, so that simplifies further to f of 1, f of 2, f of 3, f of 4, all the way up until we get to, if you distribute, distributing a positive, you're just dropping the parentheses, f of n. All right, so whatever the nth value is, that would dictate what that last term ought to be based off of the substitution. All right. So instead of writing f of n, we'll write f sub n just to make life a little easier. We name our functions f, g, h, just the same way that we normally would for ordinary functions. And common names for sequences are a, b, c, beginning of the alphabet. All right. So if you're asked to find the domain of a sequence, it really just boils down to your knowledge of functions, but just bearing in mind that you're only working with positive integers. All right, so in this case here, I'm looking at, well, I don't want to have negatives under an even radical. All right, so I want n minus 4 to be greater than or equal to 0. So I want n to be greater than or equal to 4. All right, so we need to be a little bit more specific than that. All right, so the way we would state our domain would be that we're working with n such that n belongs to the set of positive integers. The integer symbol is just kind of a funny z with an extra crosshatch, or at least that's how we just draw it, with a little plus sign. And all right, so it's got to be a set of positive integers, but also n has to be greater than or equal to 4. All right, so that would be our domain. Now, in terms of the first 4 terms of the sequence, well, the first term would be a sub 4, then a sub 5,
a sub 6 and then a sub 7. So the fourth root of 4 minus 4 is going to be 0. The fourth root of 5 minus 4 is going to be 1. The fourth root of 6 minus 4 is going to be the fourth root of 2. And the fourth root of 7 minus 4 is going to be the fourth root of 3. So it's really the fourth root of 0, the fourth root of 1, fourth root of 2, fourth root of 3. But some of them could be simplified. All right, so it's not too bad when you kind of consider it that way. Now, for B, you see, or number 2, which is B, you see that there is no radical, but there is a denominator. So we would want that to not be equal to 0. So 3n minus 2, I don't want that to be equal to 0. So 3n can't be equal to 2, in which case n cannot be equal to 2/3. All right, so you'll see a lot of similarity when it comes to the domain. I'll forevermore write domain as d colon. N is the variable such that n belongs to the set of positive integers and n cannot be 2/3. All right, the first 4 entries. Well, we want positive integers. All right, so we would start off with a 1, then go to a 2, go to a 3, but we got to make sure that we don't hit a 2/3. Well, fortunately, it's irrelevant. All right, so when you think about it, by saying that we're dealing with the set of positive integers, we are in fact stating that this would be excluded anyway because that's not an integer. So therefore, my domain could be simplified to n such that n belongs to the set of positive integers. All right, so my first entry would be, if my pen decides to work, b sub 1, b sub 2, b sub 3, followed by b sub 4. So 1 plus 4 is 5. 3 times 1 is 3, minus 2 is 1, so just a 5. 2 plus 4 is 6. 3 times 2 is 6, minus 2 is 4, so 3/2. 7. 3 times 3 is 9, minus 2 is 7. And 16 over 12 minus 2 is 10. So we're talking 8, I almost said 5/8, so 8/5. Right? The challenge is going to be essentially going the other way, because when I said earlier that this is really the same as saying the fourth root of 0, the fourth root of 1, the fourth root of 2, fourth root of 3, you can see what the pattern is. Here it's like, okay, well, what is the pattern? So, if you were just given this relation, are you going to be able to pull that from it? That's the trick, or the challenge. All right. Now, there is a way of verifying this information. What you can do is you go into mode and select sequence. Then you hit y equals, put in your minimum. So what the domain is important. So you put in whatever the minimum is for your domain. Then that xt theta n key is going to present you with an n every time you hit it now. So I'm going to type in n plus 4. So n plus 4 divided by 3n minus 2. And then I'll just go into the table, and you see that the entries are 5, 1.5, which is 3/2, a 1, and an 8/5. All right, so 8/5. Okay, so I definitely screwed that up. All right, so let's see. 4, 8, 4 times 3 is 12, minus 2 is 10. So 8/5. That's not 0.8 though, is it? No, it's not. 4 plus 4 is 8. 3 times 4 is 12. This is interesting. Interesting. Come on. Come on. Okay. It's funny. In my mind, out loud I kept saying 4 plus 4 is 8, yet I kept writing 16. I have no idea why. Subconsciously, I wanted to write the 8, but I don't know why I didn't put it there. So yeah, that's going to be 4/5. Yeesh. Got there eventually. So, that shows the benefit of checking your work. I'm not even going to edit that out. All right, so maybe it's actually a little easier now to see what the pattern is, but still, it's definitely worth spending some time to consider the unsimplified forms and how they relate to one another. So the numerator is 5, 6, 7, 8. Very easy to see the pattern. 1, 4, 7, 10, starting off with a 1, increasing by 3 every step of the way. All right. Which, when it gets to simplified form, it becomes more difficult to see. All right. Now, number 3, it looks like we have a little issue here. We don't want n minus 6 to be equal to 0. So n can't be equal to 6. So our domain has to exclude that. So n such that n belongs to the set of integers, positive, and n is not equal to 6. All right, so we're good there. They're only asking for the first 4 values. So we're fine. If we needed to go further than that, we'd have a problem though. All right, so C1, 2, 3, and 4, what we're looking for here. Now if you put in a 1 as the exponent, -1 to an odd power is going to be -1. So I'm going to have a -1 for all the odds. +1 for all the evens. That's going to give us what's called an alternating sequence. All right, goes from negative to positive to negative to positive, and so on, or maybe the other way around. Plug in a 1 for n in the numerator, you get 4 minus 1 is that's going to give you a 3 over -5. So we're talking 3/5. All right. Plug in a 2, you get 8 minus 1 is 7 over -4. We're talking -7/4. Plug in a 3, 11 over -3, positive 11/3. You see how it's alternating back and forth between negative and positive. All right. I'm a little more cautious about my computations now, so I'm definitely checking this on the calculator in a minute. So if you notice a mistake, just bear with me. All right. So plugging in a 4, you got 15 over -2, so we're talking -15/2. Although, that being said, looking at the denominators, I'm feeling pretty good about this sequence here because the denominators are decreasing. All right, so should that be the case? I don't know, but it's a pattern, and anytime a pattern emerges, I feel pretty good about things. All right. In terms of the numerators, it looks like if we disregard the negatives that we're increasing by 4 every time. So that the negatives are accounted for by the -1 to the nth power. So let me put this in. -1 raised to the nth times the fraction. Oops. -1 raised to the nth times, come on, okay, there we go, 4n minus 1 over n minus 6. All right, starting with a 1, so we're good there. Go into our table, 0.6, we're good there. This is the same, yeah, that's -1 3/4. 3 2/3, yes, 3 times 3 is 9, okay. Negative 7/2, so we're in good shape here. Now you'll see here when you get to 6, you get an error. And then actually, as it turns out, anything beyond that, based off of what the calculator is saying. But for our purposes, it's only the 6 that we would care about, because that's the only thing that would make it undefined. Once it goes undefined, it can't be defined again, right? Unless you start with your initial value on the other side of the point of discontinuity, or for lack of a better term, point of discontinuity, because this is a discontinuous function to begin with. These are only points plotted in space. They're not actually connected, all right? So let me see if it's easy enough to show you. It's because of the undefined term, it's a little tricky. Maybe a different problem would be the way. You know what? I can just modify this one. Let me just actually start it at 7. The numbers are going to be pretty. Yeah, they're pretty large. Okay, so let me get a window here. So 7, they're going 7 to 10. Let's make it 7 to 20. X min. Let's make that negative 10 to 10. Negative 10 to 30. And you can see here that we have some alternating points. So I just expanded it outward. I can go up and down a little bit more, but I just wanted to show you very quickly that it's not a continuous function, but it does have that function feel to it like in Calc 1. All right, so these are by nature discontinuous points, but what's happening here is we have nothing in existence at n equals 6, so that's gone completely. All right. So, and then by the way, you can see the trend here. It does appear that it be converging onto something. I wonder what that would be converging onto. That's going to be the topic of discussion as we go forward. Now, in the case of number 4, there is no value of n that's going to make it undefined or imaginary, so our domain is simply, poor quality squiggly bracket, n such that n belongs to the set of positive integers. All right, so I'd be looking at, now this isn't defined as really anything in terms of, a sub n, b sub n, whatever. It's just given in the bracket form. So I would just write it as 3 over 10 to the first, comma 3 over 10 to the second, comma 3 over 10 to the third, comma 3 over 10 to the fourth. So 3/10, 3 100ths, 3 1,000ths, and 3 10,000ths. All right, so it definitely has kind of an asymptotic trend to it, but we can take a look at the graph. So starting at 1, we're looking at, again, 3 divided by, I'll just put it in parentheses, 10 raised to the nth power, I said. So I'll do a standard zoom, and you see really nothing shows up if you do the standard zoom, because yeah, it's going from 1 to 10, but in terms of your x min, x max, we're looking at some pretty large values. The first value that we have here is 3/10. So let's make our y max something closer to like 1, and let's ignore any negatives for x min, and maybe only go out to, we could leave it at 10. Right. Oh, actually, I just realized that I didn't change my y min. All right, so you got a point here. It's hard to see, but there's a point there. The next one is 3 100ths. So it's even harder to see this one, but you see how there's little tick marks here that represent the scale? This one's a little taller. That's actually the second point.
The third point is even close. It's 3/1000th of a unit, so it's virtually merged with the x-axis. All right, so very tricky to see, but it's still there. All right.